So following on from the previous video, we got to this stage here. We were trying to sketch this function here. We can now guess our function to look something like this. Okay, so now let's try and find out where the gradient will be zero. So starting with this, differentiate it to find out where the gradient will be zero. So looking at this here, our original function here, differentiate it. So blah blah blah. When you differentiate it, it will take you to here. Okay, it will take you to here. So now find out when the gradient will be zero. So let f of x here equals 0. Okay, so let this whole thing here be 0. We are trying to find out where the gradient will be 0. So now visualize it as one bubble here divided by this bubble. So times both sides by this bubble here. That would then give you this. So looking at this, x must equal 0. So what that means is the gradient will be 0 at x equals 0. So that means we now know the gradient here. The gradient here is 0. Okay. So now we need to looking at this. So far we know that it's going to do something like this. Okay. So the gradient here will be 0 here. Right in this region it will be 0. Okay. So now looking at the gradient, let's try and analyze this gradient here. So looking at this, we can looking at our derivative here, our first derivative, we can deduce what happens over here and over here when x is big. Okay, so let's analyze this this f prime here. When x gets very big, look at this here. Hang on, we can imagine this as we can imagine this as x to the power of 3. Okay, because when if you look at it, x to the power of 3 looks like this. X to the power of 3 plus 2 looks something like this. Let's just assume that this thing here is x to the power of 3. Okay, so when x gets very big, we can think of it as being like this. Hang on, you see what I mean later on. Bear with me. So this bubble here, we're going to visualize it as x to the power of 3. Okay, and then you power it to 4 over 5, and then this gets multiplied with this. So that then becomes, hang on, that then becomes x, and then 12 over this thing here. You see, this thing here will always be bigger than this thing here. Whenever you have this thing here, hang on. When you compare the two here, this thing here will always be bigger than this. Okay, it's a bit like me saying this. It's a bit like me saying this thing here is bigger than this. It's a bit like me saying that. Hang on. It's a bit like me saying that this thing here. Let's say this thing here will always be bigger than this. It's a bit like me saying. Hang on. It's a bit like me saying this thing here will always be bigger than this thing here. Okay, so hang on, let's start again here. When x gets very big, we can imagine this thing as hang on, we can imagine this thing as being x to the power of 3, because x to the power of 3 is slightly less than this. But let's assume the worst case scenario. Let's just say it's x to the power of 3, and then we're going to power it to this. And then this then becomes this thing. The point I'm trying to make is that you would get to this thing here, 12 over 5 here. This thing here will always be bigger than this. So as x gets very big, this thing, the number at the bottom here, the denominator will run away from this number here. So as x gets very big, the denominator will get much larger than the numerator. So making the whole thing here head. It will make the whole thing here head towards 0. So what that means is if x gets very big, and then f prime heads towards 0, what that means is that we can deduce that the gradient will be very flat as x gets very big. So here it really confirms to what we guessed earlier. So rather than it climbing up like this, rather than our graph climbing up here, we know that as x tends towards infinity, it flattens out. The gradient will head towards 0. It flattens out rather than the graph doing something like this. The gradient here is not flattening out. Whereas if you have it something like this, then you can say the gradient is flattening out. Well, you can't really say that, but we can say that the gradient is heading towards 0. So looking at this here, as x gets very big, this whole thing here heads towards 0. So if it heads towards 0, then we can say that the function itself is flattening out as x tends to towards infinity. We can say that the gradient here is heading towards 0. Okay, so we now know it flattens out, and then you can use the same argument in this direction as well. Okay, and you can also deduce that the gradient here will always be positive. Looking at this, you can actually deduce that the gradient here is flat. Well, the gradient here is very low, but it's positively low, so it's climbing, but it is low. You can actually deduce that if you stare at this long enough. Okay.